Good morning, everybody. I'm sure most of you are not familiar with Tenebraex Corporation. Tenebraex Corporation is a company that's been in business in Boston, Mass. For about 15 years and got its start, and its mission is to create optical technology that solves real-world problems. It got its start in developing camouflage for optics for the military, so to get rid of reflections off binoculars and laser filters and such. Tenebraex has manufactured and sold over 1 million of these that are deployed throughout the world with our Army and special sources. Also, Tenebraex Corporation developed color night vision. Night vision, as you know, is made with a monochromatic green tube, and the images look like that. They're monochromatic, and you can't distinguish colors. You can't distinguish different things within the image. What color night vision does is utilize Retinex technology developed by Edwin Land to distinguish colors and pull the color information out of a standard tube. So in this particular image, you can see that what appeared to be just some kind of water on the shirts is now really blood and water. And so this is being used right now as a test in the military to help save lives for our soldiers. Out of that research, Tenebraex developed iPilot, which are software tools that help colorblind computer users. And so that represents 12% of the male population. And what iPilot does, for example, in a map like this that's color-coded, this has no meaning to someone who has color blindness. And so what happens is that if you use the tools, you can pick out areas of a particular color, highlight them, and not lose the context of the map. But today, I'm here to talk about a new development in technology that we're working on, which is called distributed imaging. We have spun off a new division of Tenebraex Corporation called Scallop Imaging, dedicated to creating the new technologies and products using distributed imaging. So what is that? We're all about breaking the film paradigm. You say, what's the film paradigm? Well, the film paradigm is if you want a better picture, you need a bigger piece of film. And if you're going to use a bigger piece of film, you need a bigger camera. And here's our founder, Peter Jones, with his homemade 20 by 24 camera that he still has today. But the difficulty in using the film paradigm and applying it to digital imaging is that the film model does not really scale that well in the digital domain. One example of that is when you buy a bigger piece of film, the cost of the film scales as the area of the film. But that's not the same with image sensors. With image sensors, the cost scaling is far more exponential. So what does Scallop Imaging do about that? We believe the future of imaging is distributing the imaging task. This is not a new idea. It's been widely done in nature, like this jumping spider. Or the scallop, which we take our inspiration from, is lined with a lot of little image-forming eyeballs that are utilized to create an awareness of the creature's surroundings, even though it doesn't have a brain. So what are some of the application areas for distributed imaging? One is developing 180 and 360-degree field of view camera systems, also for ultra-high resolution, super resolution, and multispectral imaging, all with a manageable bandwidth. Our first product that you can see outside at our table is called Digital Window. It's a new development in surveillance cameras. Digital Window has a lot of advantages. It's an ultra-low cost based on using miniature camera modules that come out of cell phones, has a full 180-degree field of view with no optical distortion, very high resolution, and greatly reduced bandwidth needs because our high-speed video interface simultaneously puts together a low-resolution situational awareness image and a high-resolution zoom window at video rates. This is what digital window looks like. You can see that we have a number of different little eyeballs looking in different directions, along with its associated electronics and interface. So just to give you an idea of what this approach buys you, this picture was made with a current state-of-the-art 3-megapixel axis wide-angle security camera, and you can see the optical distortion. This image was made with our D7 7-megapixel security camera head, where you can see that it creates a true 180-degree image with no distortion. If you look at what security cameras need to do, which is to identify people within the image, you can see that our 7-megapixel security camera head is far superior. And the Axis camera has a price of around $900, where ours is much, much less than that. Look at the size and the inherent bulk of the product. The digital window is much smaller, much more compact, and it will never require that great big piece of glass fisheye lens, which drives the price of the camera. We're also looking at miniaturizing this for automotive and other applications, using a number of very small VGA camera modules ganged together. And now I'm going to talk a little bit about going in the other direction, which is extreme definition imaging. The current highest resolution available in a non-scanning camera back is around 50 megapixels. And those cameras run around $40,000. There's a growing popularity of very high-resolution imagery. I'm sure a lot of you have been out to gigapan.org. But the image quality created conventionally with panoramas is limited by the sequential nature of taking pictures. It might take 20 minutes to get all those pictures taken, and light changes and things move, so that limits the quality. We have developed a prototype, which we call the Paradox Extreme Definition Panorama Camera. And in this particular one, we combine the output from a number of different image sensors using one lens for each sensor. Here's a picture of our prototype out here yesterday, gathering some image data. So we have a number of different cameras looking in different directions. And this is the kind of imagery that you can get with this camera. And it's hard to appreciate, I'm sure, on the display here, but you can come out to our booth and our table and take a look at it. What's nice about this is as you zoom in, you have more and more rich detail, and zoom in again and more detail, and it doesn't break up and it just doesn't quit. We're very excited about it. But 54 megapixels is nice, which is what this camera is, but why not go for it with 300 megapixels or more? One way to do this is with a sparse array of image sensors under 4 lenses with large image circles. So for example, given package size versus active array and all that other stuff, you can do the geometry and come up with a sparse array that, when interleaved and stitched together, will give one very, very high resolution image. And here's a camera concept that would be made using that approach. So what does that buy us? Here's a picture that's taken outside our office window in Boston, and I'll direct your attention to that tower in the background, the glass tower. It's a hotel. Well, we took that picture with a D300 camera, which is top of the line, and it's absolutely beautiful, and when you zoom in, you see a very nice, sharp picture. When you take the same picture using the 300 megapixel, the detail is incredibly rich and doesn't quit. So if you could imagine this entire field of view with that level of detail, it puts it in a completely different category for imaging. So in summary, at Tenebraex Corporation and Scallop Imaging, we believe the future of imaging is distributing the imaging task, and we invite you to come to our table and take a look at some of the images in our hardware. Thank you very much.